Now, we've selected our controller to be a PID controller because it drove the steady state error to 0 for any gain that we chose. Then we selected what the dominant poles were that we wanted in our closed loop transfer function based on the rise time and the maximum overshoot that we wanted our output to have. So what we came down to was, for a PID controller, that we get to choose 2 zeros for the system. So we know that the Z1 and Z2 that we choose for this system, when we add those angles together, they have to add to the -7 so that the closed loop transfer function will have the poles that we desire. So we're going to go through 2 different designs that should achieve this, at least in theory. So I'm going to select for both of these designs that the zeros I choose for my controller will be complex conjugates of each other. Now, they could be both real, or they could be complex conjugates. I'm not going to go through real examples in either of the designs, so I'm going to say that they're in the form of A plus B times J, and then the other is A minus B times J. So, for the first design, I'm going to choose the real part will be 1.6. In general, if we choose the real part of the 0 to be close to the real part of our dominant pole, it should have more of an effect than if we choose a 0 that is further away, using kind of that 4 times rule that we looked at the in Unit 2. However, for this system, that's not necessarily going to be the case, as we'll see a little bit later, because we're actually adding 2 zeros into the system. So I'm really just arbitrarily going to choose 1.6 to be the real part of the 0. Now, this is, again, going to be close to the real part of my pole, -1.15. But we'll see in simulation how this pans out. So if I say that the real part of my pole is 1.6, I can put that in for Z1 and Z2, since again, they're going to be complex conjugates of each other. So at this point, if I put that into my equation, now I have only one unknown, the value of B, which is the imaginary part of the 0 for my controller. So I have one equation for one unknown, the value of B. Now again, by definition, the angle is the 4-quadrant arctangent of these 2 angles. So I'm adding one arctangent to another arctangent, and that's going to be equal to -7. At this point, it becomes solving for B is not trivial, because I can't simply take the tangent of both sides, because on the left-hand side, I have the sum of tangents. Well, the tangent of a sum is not the same as the sum of tangents. So I can't simply solve it by taking the tangent of the left-hand side and the tangent on the right-hand side. Really, I need to solve this numerically, unless I have a very clever analytic way of doing this, but a numerical solution for B is going to be just fine. And to do that, I'm going to take this equation and put it into MATLAB. So I can express that equation 2 different ways in MATLAB using the arctan2, or in MATLAB, I prefer to use the angle function because I can have real parts and imaginary parts. So I show on line 9 using the angle function, but I'm also showing it here the same thing if I wanted to use arctan2, but then I have to put in manually what the imaginary parts are as the numerator and what the real part is as the denominator. So let's look down here first. All right, so the highlighted portion at the moment is what I had on that slide once I put in the real part of my 0 was 1.6. So I have the angle of the first term, and I have the angle of the second term. Now, but my desire was that the sum of these angles was -7 degrees. To solve this numerically in MATLAB, one way we can do it is using the fzero function, like I'm showing here. But the fzero function requires that is finding the 0 of a function. So I don't want the sum of these 2 angles to be 0. I want it to be -7 degrees. F0 is not set up that way, but what I can do is cheat a little bit and say, well, instead of the -7 being on the right-hand side, what if I put it on the left-hand side? And if I add 7 degrees to the left and the right, now my right-hand side is 0. And then I just have to add 7 degrees to the left-hand side. So that's what I'm doing here. I'm adding 7 degrees. And I'm putting everything here in radians because that's going to be the default when I use this angle. So now this highlighted part is what I want to find the 0 of. If I find the B that makes this 0, That means I found the b that made the sum of those two angles -7 degrees, because what I would have here is the sum of the angles is -7 plus 7 equaling 0. So this function is only 0 when I'm adding -7 to a +7. So what I'm doing here using this fzero function is this is the thing I want to find the 0 of, and I'm telling it up front that b is going to be the variable that fzero should be changing until that's true. And then over here, I'm giving an initial guess as to what I think the value of b is. So here, I don't necessarily know up front what it should be. I'm going to try 1, and I'm going to let fzero tell me what the right answer is. Now, depending on how difficult it is to find what that value of b is, I might need to try different starting points. But let's see if 1 works. So I'm going to run this, and it's going to tell me the b that makes this true. All right, so applying fzero here, this is telling me that 4.44 is the value of b that makes that expression true. So putting that value of b, the imaginary part of the 0, back in here, this tells me that the zeros I want for my controller are then 1.6 plus and minus 4.44j. And since the total angle added up to 180 when I put these zeros in, this ensures that my desired closed loop pole of -1.15 plus minus 2.11j will appear on the root locus. So let's see what is the transfer function for that root locus. So going back to that g prime, now that I know z1 and z2, I can put those into the numerator. I can distribute, I can FOIL, I can expand everything out. So the g prime, the thing for the transfer function, is s squared plus 3.2s plus 22.3 over s squared plus 2s. So now I'm going to take this g prime and I'm going to make its root locus. And I'm going to do that back in MATLAB. Now, going back into MATLAB, I'm going to use the same code basically for both of my designs, as we'll see in a second here. But I'm going to start with design number 1. So really what I'm going to do is I'm going to define my root locus transfer function here. I'll call it GL in this case, is going to be that 1, 3.2, 22.3 over 1, 2, and 0. So that's the exact g prime that I just showed on the slide. It's just going to be in the transfer function form. So if I just run that, we can see that it's identical to what was on the slide. So that's what I'm going to do the root locus of, and I don't know up front what the gain should be. So I'm going to start with a pretty seemingly low gain of 0.01, increase it very little by little until it's at 1. And I'm going to see what gain it takes to get to my desired pole location. All right, so I'm going to run this and make the root locus. All right, so here's the root locus for this g prime, which I got for this selection of zeros for my controller. So I want to find my desired poles of the -1.15 plus minus 2.11j. So again, I only need to find one of them. So I'll just do the one on this blue line. All right, so if I keep increasing the gain here, we can see that the pole is shifting slowly. I'm going to take this just to 2 digits. I see that I can get a pole of -1.15 plus or minus 2.08j if I have a gain of 0.34. I can't really get any closer to the more precise pole at 2.11j. That's because I did round a little bit when I put that b in. I only put 4.44. So I'm not going to be able to get exactly the closed loop pole, but this is really as close as I'm going to get, and it's going to be close enough because there's other sources of error anyway. So I'm selecting here a gain of 0.34 to get pretty close to that closed loop transfer function. Right, so for my design 1, I chose arbitrarily a real part of my 0 for the controller to be 1.6. Then I found that 4.44 should be the imaginary part. So those were the 2 zeros for my controller. I made the root locus using the root locus transfer function and just found that the gain should be 0.34 so that my closed loop poles were at -1.15 plus or minus 2.11j, or pretty close to that. So now to implement my controller in my next step, I'm going to take this general form on the left-hand side, and I'm going to expand it out. And because it's a PID controller, I'm going to get is a constant term, a term times s, and a term over s. So when I do that distribution, I find that I have 1.09 plus 0.34s plus 7.57 over s. What these three coefficients tell me are what the three gains should be for my implementation of the controller in the next step when I head into Simulink. So Kp, the proportional part, is just the constant. Kd, the derivative part, is the term in front of s. And the Ki, the integral gain, is the term that is over s. So these are the three gains I'm going to use in my simulation to validate this design. So now going into the Simulink model for this, it looks similar to the controllers that we were using before, but now I'm going to take my error and I split it into three parts. Part of it is, or one branch goes through the Ki gain and then through my integrator, the 1 over s. One goes through my proportional gain and then just straight through, and one into my derivative gain, and that goes into what I'm calling my s. But remember, to implement this, I can't just have a transfer function that's s. It's s over a very small coefficient plus 1, and that's going to effectively be s, or do a derivative. Then I'm going to sum those three parts together. Now, because I'm using a derivative controller here, I am going to put in a saturation or a limiter, which practically I would have to have on my controller because I can't provide infinite input voltage or input effort at any time. So what I put in as my limiter, as my saturation, really does affect how good this controller is going to be. If I could put a very high maximum input in, then the derivative kick at the beginning is really going to change the behavior versus having a smaller limit. And we'll see that in a second here in the simulation. So I'll put a value in here for the limiter of plus or minus 20 volts. It seems fairly reasonable, but I'll put in a much larger value and see how that really does affect the performance of the system. But this is going to be dependent really on the hardware you would have in your system. So I'm choosing 20 and negative 20 here somewhat arbitrarily, and we'll see how it performs. All right, so then that's the actual EI, or input, that goes into my plant, and then I'll see the output. So like before, I'm going to have the things I'm going to be able to monitor here be my error, my output of the system, and the input going into my system when I do my simulation. All right, so I'm going to run it like I've done before with looking at these simulations. I'm going to run my simulation using the sim command. I'll run this for 7 seconds. Could be shorter or longer. We'll see what the results look like. And then I'm going to plot the results out of this. And what I'm interested in for the validation, once I go to the end here, is I care about the max overshoot. So I'm going to calculate that. And I care about the rise time. So remember, the way that we're defining rise time, it's the time it takes between being at 10% of the steady state value and being at 90% of the steady state value. So in 87 and 88, I find the first time that I surpass 10%, that's at line 88, and the first time that I surpass 90% of the steady state value. And then in 89, I find the time between them, and that's how I'm going to numerically calculate my rise time. So I'll run my design through the simulation and see the results now. All right, so here's our output and our input for this design. All right, and then I have the calculations down here. So this calculated my max overshoot to be about 18.4%, and it calculated my rise time to be 0.64 or 0.637 seconds. And if we look at the input on the bottom, it does immediately spike up to that maximum of 20 and then comes down pretty quickly. And then we see it follows through and doesn't even go above about 14 volts again for our input effort. But that limiter, we're going to see in a second, does have a big effect on how this can perform, that we can only provide that instantaneous 20 volts when we put this limiter on. So if I go back in here, let's say that we had a much more capable actuator. We could provide a lot more. I'll go up to 20,000 just for this demonstration here, so I don't have to change too much. All right, so we can provide a much bigger spike. Let's see now how it performs. So here's our output and our input. So the input goes up to that maximum that we're calling for, and then relatively becomes very small. And we see that the output is also looking pretty different. And our calculations, if we could provide that instantaneous 20,000, or here it's asking for about 2,000 volts at the input, then our max overshoot is 13.2%, and our peak time is 0.79. So having a higher limiter there, it really does change the performance, but practically could we provide an instantaneous voltage that high? No. So we have to be practical in what we could even do in hardware. And again, anytime we have a derivative control, this is going to be an issue. Can we provide the amount of kick, that instantaneous input that it's demanding? So I'll set it back down to something, again, seemingly more reasonable of 20 and negative 20. And rerun this once more and get back to the design we will consider that's a little bit more practical. Right, so seeing the results here on the slide, we see our overshoot and our rise time for this design. So again, keep in mind that these results are for this particular zeros that we chose, and then also the gain that got us to our dominant poles, but it's also dependent on the limiter or the saturation that was in the Simulink model. If we didn't have the saturation there, we would see different results. So this closed loop transfer function that we come up with does not take into account that limiter. I'm adding that in the Simulink model, but not in the theoretical portion that we're dealing with. So there's going to be two reasons why we see deviations from the theoretical. The zeros that are in the closed loop transfer function in the bottom. So we see here we have two left half plane zeros in addition to the two closed loop dominant poles, but also we have a limiter that's not being taken into account in this closed loop transfer function. So we'll compare both designs after we go through the second one and see how their performance differs.